Hi, my name is Alan Maguire, and I'm here to talk about bysyscall, bypassing system calls using eBPF. So system calls represent the interface between user-space programs and the kernel. It's when we ask the kernel to do something for us. The overhead of making those system calls, unfortunately, has grown in recent years. This is partly a result of vulnerabilities like Meltdown, which mean user space can no longer share page tables with the kernel. We have kernel page table isolation. The result of that is that switches from user space to kernel and back again are more expensive. You can demonstrate this by contrasting doing a large number of system calls with mitigations off versus mitigations on. So we take a simple system call like getPPID, call in a loop a million times, measure the total time taken, and then divide by a million to get the average time per call. And we can compare just a simple function call, a system call with mitigations off, and a system call with mitigations on. And what we see in a recent kernel is function call just takes a couple of nanoseconds. The system call with mitigations off takes about 95 nanoseconds, which is pretty quick. But then with mitigations on, we jump up to about 280 nanoseconds for that system call. So there's a bit of a growth there that you can see. There's long been efforts to reduce the overheads of such system calls. glibc used to cache things like process IDs and thread IDs, so getPID and getTID wouldn't actually require a system call. But there's problems with that, particularly forks and clones can invalidate the cache values when we're suddenly in a child process. So glibc caching was removed, and that removal caused problems too, because some containerized environments hadn't ever used the system call to get their PID, so that had to be added to the safe list of system calls. And systemd, which was a heavy user of getPID, saw some performance regressions too. Another method that's been used to reduce overheads is vDSO. So vDSO is something that's provided by the kernel. It's a virtual dynamic shared object. The kernel maps into the address space of processes. So we can see it there. There's the vDSO virtual memory area, and there's also an associated vvar area as well, just ahead of it. So as I say, the vDSO is a shared library that's built by the kernel, mapped into the address space, and its job is to look up values in that vvars area that the kernel populates. So the idea being, because we've mapped that vvars area into the address space of processes, the vDSO functions can look up the values that the kernel separately populates, and we don't have that switch from user space to kernel and back again that costs us for system calls. vDSO currently supports timekeeping and retrieving CPU ID, and random number generation has been recently added as well. So glibc uses it by getting that vDSO base address and dynamically linking in the associated functions, and then we can call them in the system call wrappers to get the data that's cached in the vvars area rather than actually having to make the system call when it's available. So when you look back at this picture, you might think to yourself, well, BPF can do a number of those things, and indeed it can. So we can use a BPF program to actually store values in BPF maps. And that sort of plays a role like vvars does for vDSO. And BPF programs can also update those values when events of interest happen. So for example, you could update your cached UID when, say, UID succeeds for a process. And the nice thing is we can also retrieve those values in user space without a system call. So we can use direct memory access for map data as long as that map has been mapped into the address space of the user space process. So at the moment, array maps support that mapping. So if we have an array map and we map it into our process address space, we can access it without making system calls to retrieve that data. So that's a nice feature. So bysyscall is essentially just a proof of concept of this approach. We're working to open source it on GitHub at the moment, so stay tuned for that. It covers a few simple get-related system calls like getPID, getTID, getUID, getGID, and getrusage. So there's a bysyscall service, and its job is to load and attach and pin BPF programs on our array map as well. And that's pinned as well to BPFFS. And then the bysyscall service just exits. So once we pinned all those things into the file system, they're not going to go away. And then to actually use bysyscall, we have to LD preload the libbysyscall library. And the reason for this is we want to override glibc's getPID, getUID, etc., with our own versions which look up cached values. So the LD preload that's essentially what that's there for, to make sure we use our own version of those functions rather than libc's. So to use it, as I say, just enable the service in the usual way, and then LD preload the library, and then you can just run whichever command you want to use. So for example, we can use Python in this case. So now when getPID is called from the Python binary, it will be the libbysyscall version, which avoids system calls where possible. So you can also enable stats. So this shows you which system calls you've avoided. So if you specify bysyscall log equals info as an environment variable, we can see here when we ran Python and just exited, we bypass get PID twice, get UID once, and get GID once as well. So we also want to assess the effects on performance, of course. So we created a simple program for each of these syscall bypasses. So for example, for getPID system call wrapper, we have a getPID program, which calls the getPID wrapper a specified number of times. Then it compares the result that we get to the raw system call to ensure that the answer that we get from our own bysyscall wrapper is right. So in a baseline case where we're not using bysyscall in the picture at all, we see if we call that getPID wrapper 10 million times, it takes about a second to do that in all. And about 2/3 of that time we're spending in the kernel. You can see the sys time there. And we can use BPF observability to confirm the system call profile is what we expect. So in this case, we see here in bold, we've got 1,001 getPID system calls for when we call that program with a parameter of 1,000. So the idea is we've called the wrapper 1,000 times and then once to verify, and we've called the system call one additional time to verify that we get the right answer. So in this case, we're not using bysyscall yet. So when we actually use bysyscall and do the LD preload, we can see the time is a lot quicker. So it takes less than 10 milliseconds to do 10 million getPID wrapper calls. And the difference there is we only spend about 1 millisecond in kernel. So we're not actually doing the system call. So we can verify that by using BPF observability again. In this case, we only see one getPID system call, and that's our raw system call that we use to verify that the answer we're getting back from bysyscall is right. So we focus for the first iteration on per thread caching of information for tasks. So bysyscall supports system calls that relate to that. So we're storing process ID, thread ID, UID, group ID, and usage data for get our usage on a per task basis. So we have an array map. As we said, they can be mappable into user space. So that's used to store this info. So each element in the array contains all of that information. And we have an index variable, and that's essentially what user space is going to use to figure out for its particular current context, which element to look up. So that index assignment needs to be done. So it's done for when libbysyscall is first used, when we LD preload it. And when we fork from a libbysyscall using process, and when we pthread create from a libbysyscall using process, because in all those cases, we need a unique ID for the unique task that we're dealing with. So one question you might ask here is, rather than using an array map, could we not just use mapped per task storage? That seems like a nice fit for a problem like this. And there's proof of concept patches for this. But the problem with that is that every time we'd fork or create a thread, then it would become expensive because we need to actually explicitly map the memory associated with that task into user space. Whereas just updating an index value is a much more lightweight approach. So you can see here, here's the getPID implementation in libbysyscall. So we're looking to see if we have per task data, and if we do, we update the stats and then look up that per task data using our per thread index and get the associated process ID. Otherwise, we fall back to using the real getPID call. So this is what the architecture looks like. So we have BPF programs updating values as needed in a similar way to the kernel does for vvars. We have an mmap BPF array map with the indexes populated for a process with 2 threads and another process with 1 thread. So we have indices assigned to each of those tasks, which are used to look up the relevant values. So just quickly, we'll kind of demonstrate how we got to this point. So initially, when we LD preload our bysyscall library, its first job is to essentially find that mmap to array map and mmap it into the user space of the process. So when we have an init function called bysyscall init, which is called when the library is first loaded, and that's essentially what that does. But we also in the kernel have a BPF program tracing that bysyscall init call. Its job is then to find a free array index in our array map, update the cached values in that array index, and then set the index in the user space process via BPF probe write user. So now we've got an assigned index which has populated data for this process and single thread. Moving on, we can fork from that process, and in this case, we actually have a uprobe tracing the return of the fork, where the return value is 0. That's when we're in the child process context. In that case, we need a separate array index again. So we find a free one, update the cache values, and set the index to 1 in the child process. And because we've got copy on write memory here, we've got a separate memory storage for the same index. So we can change that value there in the child process without affecting the parent. Threads are a bit more complicated. So in this case, we have to trace start thread, which is what the pthread library calls when it's starting to run a new thread. So in this case, again, we get an array index, update the cache values, and set the index value. We have to actually get the per thread variable address, and we get that relative to the pthread t that we're starting. So we can assign that value as well. So we've wound up with separate index values for each of these processes and threads, and we can look up the values then without actually having to make a system call because we've then mapped the memory into the address space of the user space processes. So in future, we want to support more clone variants. There's a lot of flags to clone which can do complicated things. So you want to support all of those things. We also want to look at, of course, adding more additional system call support as well. So thanks for your time.